Hello and welcome back to another stats notes. All right, so this is actually the last note video for this unit. And we're going to be taking a look at the geometric sequence. So last class was the binomial sequence. This is going to be the geometric sequence. All right, both involve this idea of Bernoulli trials, where you have either a success or a failure. The probability stays constant and the trials are independent. The difference is binomial is a fixed number of trials and you're counting how many times you succeed or how many times you win. The geometric is the situation where we're counting how many times we have to play until we win. So we don't know how long it's going to take. We're just going to keep going over and over and over again until we win. Now, at the end of the last class, we saw that there was a normal approximation for the binomial distribution, which meant that if certain conditions were met, primarily that you had 10 successes and 10 failures, and expected 10 successes and 10 failures, you could use the normal model to approximate the geometric model. So generally what we do in class is we start with a little activity to show that the geometric sequence has a very different shape, and it's something that we're not going to be able to model with a normal approximation. All right, so we're going to have to exclusively use the geometric sequence when we're going through these, or the geometric probability model. All right, so the activity is as follows. It's basically a guessing game. So in my head, I've got a number 1 through 5, and I would ask you to try to guess it. And you might say 3. I'd be like, nope, that's not right. And then I would think of a new number and ask you to guess again. And you might say 1. And say, no, still not right. And then I would think of a new number, and then you would guess again. And I would be like, oh, you got it. It was 5 or whatever. All right, so it's basically just a guessing game. Now, it's important that I change the number each time, because if I don't change the number each time, the probability changes, all right? Eventually, you'd be guaranteed to get it because you'd work through all 5 numbers. But if I change it each time, the odds of you getting it stay consistent. You have a 1 in 5 chance of guessing every single time. Now, the way we have students usually play this game, because we want to gather some data, is we use the calculator. So in the calculator, just for your own knowledge here, under probability, there is a random integer option. So if we do 1, 5, this is basically going to generate a random number from 1 to 5. So I could be like, all right, I think it's going to be 3. Nope, I was wrong. All right, this time I think it's going to be 4. Nope, still wrong. This time I think it's going to be 3. Nope, still wrong. Doesn't seem very random right now. I think it's going to be 4. Nope, at least it changed this time. I think it's going to be 3. All right, I'm doing really bad at this. I think it's going to be 4. I hate this so much. I think it's going to be 1. Nope. I think it's going to be 3. I am really bad at this. I should probably just guess 2 or 5. I think it's going to be 4. All right, I'm just guessing 2 now. I think it's going to be 2. I hate you so much. I think it's going to be 2. 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 There we go. Look at me. I finally got it. That was painful. So it just took me several tries to get it, but each time it was a success or a failure. The probability stayed constant. I had a 1 in 5 chance each time, and each guess was independent of the other guesses. I fell victim to, oh, there's been a bunch of 2s. I should probably start guessing 2, but there was no logic there. Right? Each one was being randomly generated, so I had no knowledge. So anyways, what I have kids do is I have them do that 10 times. So maybe the first time they get it on their first guess, and the second time they get it on their 6th guess, and the next time they get it on their 3rd guess, and maybe you're like me and it takes you 15 guesses. And then you get it on your 1st, or you get it on your 2nd, or you get it on your 3rd, or you get it on your 4th, or you get it on your 1st, or you get it on your 5th, or something like that. But basically, how many guesses does it take to figure this out? All right, and then we take everybody's data and we kind of assemble it into a big graph. And generally, what you're going to see is that you're going to end up with a distribution that's very right skewed. All right. And it's usually going to start highest right at the beginning and then just progressively get lower and lower and lower and lower and lower and lower and lower as we go. All right. And generally, all right, you're going to get a mean, all right, or an average number of guesses that's going to end up somewhere between, like, 4 to 6. It's generally going to be sort of in that range where it's kind of somewhere around those values. Obviously, it's a very right skewed distribution. And in theory, there is no limit to the max, all right? The smallest value you could ever have is always a 1, all right? We can't do any better than getting it on our first guess. But if, in theory, you could be the world's worst guesser and never actually get it right. Now, that becomes super unlikely. After 100 guesses, chances are you're going to get it right sooner or later. But you could be the world's unluckiest person and in theory, never get it right because a new value is being selected each time. So expected value is also called the mean. We know that hopefully at this point. But that's sort of the activity that we would have done as a group in class. But this is the end result of that activity, all right? It's a graph that you're seeing is very right skewed. We're going to see that it generally averages somewhere between 4 and 6. The smallest value you can get is a 1. The largest value, again, it depends on how poorly you did. But in theory, it could go up to any actual value there. All right, so either way, you can see that this is not normal. All right, this is clearly not a normal curve, and we're not going to be able to use a normal distribution to estimate probabilities from a distribution that looks like this. Meaning, we've got to come up with a new technique, all right? And that new technique is the geometric probability model. All right, so let's use some math to figure out what the exact expected value would be. All right, so when we did this activity, generally I said it comes between 4 and 6, but what is the true value? How can we find the true value? Well, we've learned that, to find the expected value, it's the payoff times the probability. So, did it take 1 try, 2 tries, 3 tries, 4 tries, 5 tries, so on and so forth? Those are your payouts. And then we know the probability because the probability of success is P. So if you get it on your first try, that's just P. Like, you got a 20% chance, so you got it. If you get it on your second try, that means you failed the first time, and then you got it on the second time, or Q times P. If you get it on your third try, that means you failed twice and got it on your third time. And we could calculate that probability. It's just Q times P. If you get it on your fourth time, instead of drawing out all the Q's, I'm just going to write Q to the third times P. I failed 3 times, and then I got it on the fourth time. And if we keep going here and we say N, for an unknown number of trials, it's basically Q to the N minus 1 times P. So we can take those and we can calculate an expected value for that. All right, so remember, expected value questions, we multiply the X value by the probability and add them all up. So we've got 1 times P, the value times the probability, plus 2 Q times P, plus 3 Q squared times P, plus 4 Q to the third times P. And technically, this goes on forever and ever and ever and ever. Because again, if you were the world's worst guesser, there is no limit to how many times you might have to guess to get that number. All right, now we're going to do a little like mathematic substitution to simplify this down. So everywhere we see a p, we're just going to substitute in 1 minus q. Again, because p is 1 minus q, q is 1 minus p. You could go in either direction there. So we're going to get rid of all the p's so that we only have a single variable. So we're going to do 1 times 1 minus q plus 2 times q times 1 minus q. Almost made a p there, but 1 minus q. Plus 3 times q squared times 1 minus, I keep wanting to make a p there, but that's a q. Plus 4 times q to the third times 1 minus q. And again, that would go on and on and on and on forever and ever and ever. All right. So now we could distribute out. All right. And this would become 1 minus q plus 2q, all right, because I'm just distributing, 2q minus 2q squared plus 3q squared minus 3q cubed plus 4q cubed minus 4q to the fourth, and it would keep going and going and going and going and going like that. All right. Now, if we were to combine our like terms, we're going to see that a lot of these things cancel out. So I have a q here and a q here. So this just becomes 1 plus q. All right. I have a 2 squared and a 3q squared here. So this just becomes plus q squared. All right. I have a cubed and a cubed here. So this just becomes, q to the third. I'd have a 4 here, and I'd have a 4 on the other side, so this would just become q to the fourth. And again, this would keep on going and going and going. So notice this is a geometric series, all right, because these are all really fractions here. These are all decimals. And remember, the sum of a geometric series can be found using this formula right here. So effectively, this whole sequence here can be reduced to 1 over 1 minus q, or 1 minus q is the same as p, so just 1 over p. So as scary as all of this math looked when we went through it, all it's saying is that the expected value for a geometric distribution is found by 1 over p. So if we go back to our game, it says the true expected value of the number of guesses until a success is 5, right? Where is that coming from, right? Our formula for mean is 1 over p, all right? The probability of success is 0.2, because if there's 5 numbers, you have a 20% chance of guessing it. So 1 over 0.2, or the expected value or the mean is just 5. And then this says how far off is the class, and it usually varies. Some years it's smaller, some years it's larger, but it's usually somewhere in like, the 1 to 0.5 range. Our class isn't big enough that you're expecting to get exactly the right value, but you get in the general ballpark. All right, so this right here is nothing I'm ever going to ask you to reproduce. It's just showing you the math behind why this is the true expected value. All right, so this is the part that you need to actually remember. That's the part that you're going to need for problems and calculations. This is just showing you the derivation of where that comes from. And then down here is the standard deviation. So what I want to write underneath here, just to make sure that we're totally clear, is that when you're dealing with a binomial distribution, your mean is n times p, and your standard deviation is the square root of n times p times q. When you're dealing with a geometric distribution, your mean is 1 over p, and your standard deviation is the square root of q over p squared. All right, so it's important that you can identify the correct distribution and then use the appropriate formulas for that distribution. So let's take a look at what we have here. All right, same example, but this time we've got our actual probabilities inside of it. All right, so we can see the probability that we are successful on our first guess is 0.2. Right? The probability that we're successful on our second guess is 0.8 times 0.2, or 0.16. The probability that we're successful on our third guess is 0.8 squared times 0.2. So that's basically 0.64 times 0.2, or 0.128. And you'll notice that these keep getting smaller, right? And it's always going to work that way. Your first trial is always going to have the highest probability, because after that, you're always multiplying, two fractions or two decimals. So they're only going to get smaller and smaller and smaller, which is why your curve starts at the highest point, and then it only goes down from there, because each one becomes less and less likely, because you have this extra step that needs to happen for it to be true. Now, the mean is just 1 over p. So in our case, we already did this, but it's 1 over 0.2. That's our probability of success. So that's 5. Our standard deviation is going to be the probability of failure, which is 0.8, over the probability of success squared. So 0.8 divided by 0.2 squared, and then you have to take the square root of that. So 0.8 divided by 0.2 squared gives you that. And if we take the square root of that, you get 4.47. So over here, you've just got the various sort of formulas. P is the probability of success. Q is the probability of failure, which is always 1 minus P. The probability of success on the xth trial, so like the third trial, the second trial, the first trial, is just failures times successes. And the failures, this x minus 1 is basically saying, okay, on the first guess, there were 0 failures, so it's just P. On the second guess, that means you must have only failed once, so it's Q times P. On the third guess, that means you must have failed twice, so it's Q times P. That's what this x minus 1 is saying, all right? If it's your third guess, that means you failed twice and then succeeded. If it's your 100th guess, that means you failed 99 times and then succeeded. So that's what this x minus 1 is showing. And then again, we just have our mean and our standard deviation formulas here. So let's take a look at a couple of problems that make use of this. You are one space from the finish of a board game where you have to land exactly on the finish or not move at all. How many turns until you finish? What is the standard deviation? So again, this is basically just asking for the mean, and it's asking for the standard deviation. So our mean is just 1 over p. Our standard deviation is q over p squared. All right. So 1 over p would just be 1 over point. Oh, sorry, not 0.2. That's the last problem. All right, we're rolling a die here. It actually doesn't say that, but we are rolling a die here. So that basically means that there's a 1 in 6 chance of getting what we need. All right, so my mistake for not specifically stating that, but we are rolling a die here. So there's a 1 in 6 chance of getting what we need, which basically means we're expecting it to take 6 turns. Now, it's not always going to take 6 turns. What's the standard deviation on this? It would be the square root of 5/6 divided by 1/6 squared. All right, so on your calculator, I could be like, all right, it is 5/6 divided by 1/6 squared. All right, that gives me 30. Take the square root of that, and we get 5.477. So we'll say 5.477. So again, just using those values, plugging them into their formulas, and seeing what it spits out. All right, what do we have here? So we're back to Postini, the email company that we looked at last class. All right, so again, they're monitoring internet messages for spam and saying that 91% of emails are spam. So let's assume that your inbox follows that same pattern, that 91% of the emails you receive are spam. And if you didn't have a filter, those would all end up in your inbox. All right, since spam comes from many different sources, we consider those messages to be independent. So overnight, your inbox collects emails. When you check your email in the morning, about how many spam emails should you expect to have to wade through and discard before finding a real message? What's the probability that the fourth message in your inbox is the first one that isn't spam? All right. So when it says how many emails should you expect to have to wade through, that's another way of saying what's the mean. All right. So again, for that, we're going to use 1 over p. All right. So the probability of getting a real message is 9%. Now, where did that come from? If 91% are spam, that implies that 9% are real. So this is 1 divided by 9%. And when we do 1 divided by 9%, we end up with 11.1 repeating. So this would be 11.11. All right, so that would be the expected value. Now, the second question is, what's the probability that the fourth message in your inbox is the first one that isn't spam? So this is basically saying, what's the probability that X ends up being 4? Right? It's 4 tries until you find an email. Right? And it's pretty simple. It's the first one is spam, which happens 91% of the time. The second one is spam. The third one is spam. And then the fourth one is the actual real email. So we're just doing 0.91 multiplied 3 times because I had 3 failures, and then 9% for the last one. So on the calculator, I'm just going to type that in as 0.91 to the third power. And then I'm going to multiply that by 0.09. And I end up with a probability of 0.0678. All right, so the probability that I get it exactly on my fourth message is 6.78%. All right, that's not the probability that I get it within the first 4 messages. That's the probability that I get it on exactly the fourth message. So let's take a look at another one. An experiment consists of rolling a die until a prime number is observed. How many times do you expect to have to roll the die to get your first prime? And with what standard deviation? So to be able to answer this question, we have to know what a prime number is. So prime numbers are numbers that are divisible by 1 and themselves. And the one that always trips kids up is that 1 does not count as a prime number because it is itself. So the only prime numbers on a die are 2, 3, and 5. 6 is even and can be divided by 2 and 3. 4 can be divided by 2, and then 1 doesn't count. So effectively, that means we have a 50-50 chance of getting a prime number. So when we say expect, that's telling us that we need to know our mean, which again is 1 over p, which in this case is 1 over 0.5, which in this case is 2. And then it asks for the standard deviation. So that's remembering this formula that is q over p squared. Now in this case, our q and our p actually happen to be the same thing, because if there's if half of them are primes, half of them are not primes. So this just ends up being 1/2 over 1/2 squared. All right, now 1/2 squared is basically 1/4. So if we divide 1/2 by 1/4, it's going to be 2. So we're basically taking the square root of 2, which is going to be 1.41. But just in case you want to see it all written out, square root of 0.5 divided by 0.5 squared is going to give me that same answer. All right, so 1 point, we'll say 4142. So on average, it's going to take us 2 rolls before we get a prime number, but there's some flexibility there. It's not always going to take 2 rolls. Sometimes it's only going to take 1 roll. Sometimes it's going to take more than 1 roll. But that would be our standard deviation for this distribution. All right, last page here. People with O negative blood are called universal donors because O negative blood can be given to anyone else regardless of the recipient's blood type. Only about 6% of people have O negative blood. If donors line up for random for a blood drive, how many do you expect to examine before you find someone that has O negative blood? All right, so again, expect is mean. So we would just be doing 1 over p, or 1 over 6%, or what's 1 divided by 6%? 1 divided by 6% is 16.67. All right, so we'd have to roughly talk to about 17 people before we found one with O negative blood. Now, what's the probability that the first O negative donor is found in one of the first 4 people in line? All right, so this is basically saying, what's the probability that X is 1, 2, 3, or 4? All right, so we could do this manually. We could say, all right, this one is just P. This one is Q times P. And if I add all these together, I'll get my answer. This one is Q squared times P. This one is Q to the 3rd times P. All right, and we can do this, all right? Probability of success is 6%. So it'd be 0.6 plus 0.94 times 0.6 plus 0.94 squared times 0.06 plus 0.94 to the cubed times 0.06. All right, and if we type this in, all right, 0.06 times 0.94 times 0.06 plus 0.94 squared times 0.06 plus 0.94 cubed times 0.06. All right, we will get an answer. Hold on, I just typed something in wrong, so I'm going to retype it in off camera, and then I'll start the video back up. All right, so if you type it in correctly, you're going to end up with something like 0.2193. Now, this would get super, super tedious having to do this over and over and over again. Now, we do have calculator functions that will do this. All right, if we go to the distribution menu, there is a geometric PDF and there is a geometric CDF. Now, the PDF, it's there, you can use it, but it's really not doing anything that valuable. So let's say I wanted to do the odds of getting it on exactly the fourth try. All right, the probability is 0.06. I put in 4. All right, it'll do that. It'll give me the probability of getting it on exactly the fourth try. All that is 0.94 cubed times 0.06. So yeah, geometric PDF is there. It works. There's nothing wrong with it. But the math that it's actually doing is super, super easy. You're just taking the probability of failure, you're raising it to however many failures you have, and then you're multiplying it by the probability of success. So if you get it on your fourth try, that means you have 3 failures and 1 success. If you get it on your 10th try, that means you have 9 failures and 1 success. All right, so it's there. There's nothing wrong with it, but it's not super useful. Geometric CDF is much more useful because it gets us around the tedium of having to do it over and over and over again. All right, if I use geometric CDF of 0.06 comma 4, all right, that's basically saying give me everything less than or equal to 4. So give me 4, 3, 2, and 1. And you're going to see that that will give me the same exact answer. All right, so there's that same 2.2193 that I got the first time. All right, I can also do the same thing that I did with binomial. So if I wanted to say like, all right, what are the odds that the first person is 5 or later? All right, that would just be 1 minus GOCDF 0.06 comma 4. By subtracting away 4, 3, 2, and 1, I'm left with 5 and up. So again, 1, 2, 3, 4, 5, 6, 7, all the way on to infinity. By subtracting away 1, 2, 3, and 4, I'd be left with 5, 6, and 7. So geometric CDF, very useful because it does all of this for us without the tedium of having to do it one by one. We can use the 1 minus to sort of flip things around and get those types of probabilities. Geometric PDF is there, but this is all it's doing. It's just doing these 2 little multiplications to get the answer. So whether you use it, it's up to you. But it's pretty easy to do the math one way or another. So again, geometric PDF is when you're looking for a single event, and geometric CDF is when you're looking for less than or equal to. All right. And in both cases, they're just looking for the 2 pieces of information. They're looking for P and K. They're looking for P and K. P is your probability of success. And K is your trial number. So are you trying to have it happen on the first trial, the second trial, the third trial, the fourth trial, or what have you? All right, but they both need the same information. So geometric CDF, pretty useful. PDF, it's there. It's your call. Like on this one, when we did x equals 4, we could have done this as a GeoPDF. All right, I could go and do GeoPDF. 0.09 is my chance of succeeding. I want it to happen on the fourth trial. It's going to give me that same exact answer. So whether you do it this way and you type in 0.91 cubed times 0.09. I think that's quicker than going into the distribution menu, but it's up to you because they do give you the same answer. So whatever you're comfortable with. All right, so that wraps up these notes. Again, the geometric distribution is counting how many times until your first success. It has a very different shape, so we're not going to be using any sort of normal approximation or anything like that. And it has its own formulas for the mean and the standard deviation that are distinct from the formulas we used for the binomial distribution. All right, so hopefully this was helpful. As usual, if you have any questions, just let me know, and we'll go from there. All right, bye.